Hello students and my viewers. Welcome to the series of e-lectures on signals and systems. Today we'll have a discussion on the topic of Fourier analysis, which is popularly defined as frequency domain representation of systems or frequency analysis of signals and systems. That is Fourier transform and Fourier series. We'll discuss what are Fourier transform and what are Fourier series. We'll check where we can apply Fourier transform representation and where we can apply Fourier series representation. Let's start with the discussion. What is Fourier transform or Fourier series? The Fourier transform is one of the several mathematical tools that is useful in the analysis and design of LTI systems. Another one is Fourier series. This signal representation basically involves the decomposition of signals in terms of weighted sinusoidal components or complex exponential components. These are basically the signal representation schemes that transforms a given time domain signal into its equivalent frequency domain representation. With such a decomposition, a signal is said to be represented in frequency domain. Now the question arises that why do we require frequency domain representation? The answer is very easy. Until and unless we transform a signal into time domain, from time domain to frequency domain, it will be very difficult for us to calculate the energy of a signal, power of a signal, energy density spectrum, power density spectrum of a signal at a particular frequency, and because we cannot calculate all these things into the time domain. So to calculate energy density spectrum, power of a signal, power density spectrum at a particular frequency, we need to transform our signal from time domain into frequency domain. Now, most signals of practical interest can be decomposed into a sum of sinusoidal or complex exponential components, but the decomposition should be in such a manner that when these decomposed signal again get added together, they should result back into the original time domain signal. It means that when it is basically breaking of a time domain signal into its frequency components, but the decomposition should be in such a manner that when all the decomposed signals are added again, they should result into the original time domain signal. For the class of periodic signals, which are also known as infinite energy signals, such a decomposition is called Fourier series. And for the class of non-periodic signals, which are also known as finite energy signals, the decomposition is called Fourier transform. Now, frequency analysis of a signal involves the resolution of the signal into its frequency components. That is, take an example of white light entering into a prism. The example is a very popular example of class 12 physics, that when white light enters into a prism, it is broken down by the prism action into its constituent 7 colors. Now, which when again passed through another prism which is in opposite position, they get collected and convert back into the white light. Since each color has its own frequency and wavelength, thus, the analysis of white light into its constituent colors is actually a form of frequency analysis. Similarly, here our signal waveform are all basically function of time or function of frequency, and the role of prism is being played by Fourier analysis tools, that are the mathematical tools that play the role of prism. One is known as Fourier series and another one is known as Fourier transform. The reconstruction of the sinusoidal components to reconstruct the original signal is called Fourier synthesis. That means one is decomposition. The decomposition process is known as Fourier analysis, and the recombination process is known as Fourier synthesis. If any of the sinusoidal components, that is constituent components, is missing into this recombination process, the result is a signal which is different from the original signal. So we should keep into the mind that the decomposition should be in such a manner that When all the decomposed components are added together, they should again result into the original time domain signal. So if you wish to go from time domain to frequency domain, you have to decompose the signal into its constituents components, frequency components. And when you again wish to go from frequency domain to time domain, all the frequency components when added together should result back into the original time domain signal. Now we can see that in various transformation techniques such as Laplace transforms, Fourier transform, Z transform, etc., we use a one transformation formula which converts a signal or a sequence, time domain signal or sequence, from time domain to frequency domain, which is easy and suitable for computation, and also we can extract more information in this domain which is necessary for signal processing. We also use an inverse transform formula to again convert back that signal into the time domain. Now keep to keep the information in brief, I have made a point here. What is the purpose of transformation? Very simple. Point 1 very clearly defines that there are basically two purposes of transformation. First one is for extracting more and more information from the transform domain, that is the frequency domain, for the purpose of signal processing. And we have already taken the example of a prism, white light and prism. Now, until and unless the white light passes through the prism, we will never be able to know that the white light is constituent of 7 different colors. That is known as frequency analysis. So for doing the frequency analysis, transformation from time domain to frequency domain is very important. And second one, for the purpose of simplification of computation in frequency domain. We will later on see that in frequency transformation or in Fourier series or Fourier transformation techniques, the calculations which were performed in time domain, which were very tedious and complex, becomes very easy and simple in frequency domain. We will see how it is happened in the later on sections of this discussion. So basically we have two kinds of signals. That is in the classification of signals, we have already defined that the signals can be classified as a continuous time signal and a discrete time signals. Another classification of signals is periodic signals and non-periodic signals. We will combine both these things in the analysis of signals when we are going to analyze them by Fourier transform or Fourier series, that we have already mentioned in earlier discussion, that for the class of periodic signals, such a decomposition from time domain to frequency domain is known as Fourier series, and for the class of non-periodic signals, such a decomposition from time domain to frequency domain is known as Fourier transform. But as we already know that there are two types of signals, continuous time and discrete time. So we will see that there are basically 4 transformation methods that will come in our way. One is continuous time Fourier series. Continuous time Fourier series is basically for continuous time periodic signals. Then continuous time Fourier transform, that will be applicable for continuous time non-periodic signals. Then we will see discrete time Fourier series, that will be applicable on discrete time periodic signals. And then lastly we will see discrete time Fourier transform, that will be applicable on discrete time non-periodic signals. Now before moving further, let me make you clear one very important point, that periodic signals and non-periodic signals. A signal which repeats its waveform after a certain interval of time, after a fixed interval of time, is defined as the periodic signals. And the very simple mathematical representation of a periodic signal is ft plus tp should be equals to ft, or xt plus tp should be equals to xt for all the values of time. The smallest possible value, smallest positive value of tp will be defined as time period. Now a signal which repeats its waveform after a certain interval of time is known as periodic signal. And mathematical in signal and system and signal processing applications, the periodic signals are also known as infinite energy signals, since they repeat their waveform after a certain interval of time and they go on. That's why they are, or mathematically they are defined as infinite energy signals. And the signals which do not repeat its waveform after a certain interval of time are defined as non-periodic signals. Since they do not repeat their waveform, they are also known as finite energy signals. So we'll have to clear one important point here before moving further, that one signal which is periodic